In this video, we are going to derive this interesting inequality. Let me tell you what these terms are. So, on the left-hand side, we have the magnitude or absolute value of a signal h of t. So, this is the value that the signal h has at a certain time t. We can show that this value is always less than or equal to the square root of the energy of the signal E multiplied by the bandwidth of the signal. So the bandwidth means that the spectrum of the signal will be contained inside this frequency range, which is called the bandwidth, omega 0 or omega naught. And then we simply divide by pi, that's the constant pi. In order to show this, we have to consider Fourier transforms. So we have to be able to work with Fourier transforms. And the signal h of t can be written by using its transform. So in this case, it can be obtained from the inverse Fourier transform. So we have 1 over 2 pi, and we have an integral from minus infinity to plus infinity of the transform of the signal h of t, which I will call capital H of omega. And then here we have e to the I omega t, or j. So in this case, I'm using j for the complex unit. So it's the square root of minus 1. J equal to the square root of minus 1. And then we have e to the j omega t d omega, like this. So we will start from this, and we will derive this inequality. And I will show you how to derive also the energy. So the energy of the signal is simply the integral from minus infinity to plus infinity of h of t squared dt. So this is how we define the energy of this signal, which we can show to be equal to 1 over 2 pi integral from minus infinity to plus infinity of the mode of h of omega squared d omega. So we can write it in two different ways, because this equality here is due to the so-called Parseval's theorem. Parseval. And I will write it here. But we can derive this quite easily. It's not complicated to derive that. And for a band-limited system, so we will assume that the system is band-limited, which means that, as I said earlier, the spectrum is contained inside the frequency range. So outside of that spectrum, the magnitude of h of omega will be 0. That's the assumption. And therefore, this integral here will be, yes, from minus infinity to plus infinity, but most of those values will be 0. So I can start from minus omega naught, and I can go to omega naught, because that's the spectrum. The frequencies which are relevant are from 0 to omega naught if we are considering only positive frequencies, but in the complex case, since we are considering complex functions, and for the particular symmetries of this spectrum here, this function here, which is a complex function, we have to start from minus omega naught, but there are symmetries in the magnitude of this spectrum here. So if we consider the magnitude of h of omega, we can simply reason from 0 to omega naught, because it will be symmetric from minus omega naught to 0. It's due to the properties of these complex functions when we talk about Fourier transforms. But so I will not get into those details here. We will take it as a given, and then we can obtain this relation here. So you can see that the magnitude of h of t will be, let's say, constrained. So it will be limited by the energy of the system and also its bandwidth. If we have a band-limited system, we know that the magnitude of h of t of this signal cannot exceed a certain value given by this square root here. Anyway, let's start. Let's write h of t squared, and by using the formula above and knowing how to deal with multiple integrals, we can rewrite that as 1 over 2 pi squared, and then we integrate from minus omega naught to omega naught, and we integrate again from minus omega naught to omega naught. Here we have h of omega 1, h of omega 2, e to the j omega 1 plus omega 2 times t d omega 1 d omega 2. So this is what we can do. And from this simple formula, one can also obtain straight away that formula there, this Parseval theorem. Because if you integrate this left-hand side over time from minus infinity to plus infinity, you will see that the right-hand side, when you integrate it over time, you can integrate this complex exponential. And when you integrate this complex exponential, you will get a Dirac delta. You will get 2 pi delta omega 1 plus omega 2. And when you integrate one more time over omega 1 or omega 2, doesn't matter because they are symmetric, you will get this integral here by changing just the name of the variable. So in this case, you can see from minus infinity to plus infinity. But as I said, we have a band limited system. So in here, I can also put minus omega naught, and up here, I can also put omega naught, like this. Okay, so the Parseval's theorem is really an easy consequence of, a simple consequence of this expression. Now, from here, we can easily notice that if we consider the magnitude of h of omega 1 times h of omega 2 e to the j omega 1 plus omega 2 t, well, this is equal to the mode of h of omega 1 mode h of omega 2. And from here, from this expression and also this one, it's easy to see that h of t squared will be less than or equal to 1 over 2 pi squared. And then here we will have integral from minus omega naught to omega naught h of omega mode of h of omega d omega squared. And as I said, this is a simple consequence of this expression here and the fact that if I consider the absolute value of an integral, for example, let's consider a simple single variable integral. So we have integral from a to b, f of x dx. This is less than or equal to integral from a to b, mode of f of x dx. So you can also find something similar with multiple variables. And from here, from this expression here, if you take the absolute value, you can show that this is less than or equal to that. And therefore, h of t squared will be less than or equal to this. So we already know that this is a positive quantity. So if we want to prove this, we know that this is equal to 1 over 2 pi squared. And here I can put the absolute value because I know that this quantity here is positive. So I can also put the absolute value there. So I have integral from minus omega naught to omega naught, integral from minus omega naught to omega naught, h of omega 1, h of omega 2, e to the j omega 1 plus omega 2 t. And then here I have d omega 1, d omega 2, like this. But we also know that this is less than or equal to 1 over 2 pi squared. And here I have integral from minus omega naught to omega naught, integral from minus omega naught to omega naught. And here I have the absolute value of h of omega 1, h of omega 2, e to the j omega 1 plus omega 2 times t. Sorry, let's put the straight bar here to indicate that we have to close the absolute value. So this is the magnitude of this complex quantity, d omega 1, d omega 2. We already know that this is equal to the magnitude of h of omega 1 times h of omega 2 magnitude. So we have the product of these two magnitudes. And now here you can easily see that this is equal to 1 over 2 pi squared. We can factor the two integrals because they are independent. So we have integral from minus omega naught to omega naught, mod of h of omega 1, d omega 1, which multiplies integral from minus omega naught to omega naught, mod h of omega 2, d omega 2. And of course, these two integrals are equal. You just have to change the name of the variable, and this will simply give you integral from minus omega naught to omega naught, mod of h of omega squared d omega. So this was quite an easy result to obtain, this inequality here. But now we have to do something more. So we can also show that if we consider this integral here, let me rewrite it here. So we have integral from minus omega naught to omega naught, mod of h of omega d omega squared. We can show that this is less than or equal to 2 omega naught times integral from minus omega naught to omega naught, mod of h of omega squared d omega. And we will show it straight away. We'll prove it right now. And in order to prove that, I can use the following inequality. We know that integral from minus omega naught to omega naught of a constant a, which I will assume to be a real constant, so this is real, a belongs to R, can be negative or positive, but it is real. Then I have mod of h of omega plus 1 squared d omega. So since we are summing, we are integrating over this positive quantity, we are squaring something which can be negative or positive because a can also be negative, but when we square that we get a positive quantity. So this is greater than or equal to 0. And we can also rewrite this as a squared integral from minus omega naught to omega naught mod of h of omega squared d omega plus, then we have integral from minus omega naught to omega naught of 1 d omega plus 2a integral from minus omega naught to omega naught mod of h of omega d omega, like this. And this is greater than or equal to 0. Now, this is an equation. We can also consider this to be an equation, a polynomial, let's say, whose variable is a. The variable of the polynomial is a. And it is a second order polynomial, second degree polynomial. And we know that this is greater than or equal to 0 for every a belonging to R. Therefore, this means that the discriminant of this polynomial will be less than or equal to 0. Therefore, we know that, so if we write the polynomial in this form, so we have a squared times capital A plus b times a plus c greater than or equal to 0. This means that b over 2 squared minus a times c is less than or equal to 0. So this is the discriminant of the polynomial. We can rewrite it in this form or also in this one, b squared minus 4ac less than or equal to 0. But that's the same thing, the same inequality. So this basically means that we know that b halves is this one, b over 2. So we get integral from minus omega naught to omega naught mod of h of omega d omega, and we square this. This is less than or equal to a times c. What is a? Well, A is simply this integral here. And what is C? C is this integral here, but this integral here just gives us 2 omega naught. So we have 2 omega naught times integral from minus omega naught to omega naught mod of h of omega squared d omega. So we have shown exactly this inequality here, and therefore from here we can put that this is less than or equal to 1 over 2 pi squared times 2 omega naught integral from minus omega naught to omega naught mod of h of omega squared d omega, just like this. Now let's rewrite this as 1 over 2 pi times 2 omega naught times 1 over 2 pi, and then I have the same integral. I have to cancel this thing here because I don't need it and I don't have much space. So let me cancel this. I think that this is enough. Here we have integral from minus omega naught to omega naught mod of h of omega squared d omega. But now, what is this? This is simply the energy of our signal that I called E. And therefore, this is equal to omega naught over pi times E. And we just showed that h of t squared is less than h of t squared is less than or equal to omega naught E over pi, which means that the mode of h of t is less than or equal to the square root of E omega naught over pi. So we can see that the mode of h of t is bounded by the energy of the signal, but also by the bandwidth of the signal, because if the bandwidth is very, very large, it means that we don't have really a constraint on the single values that the signal can take. Because if the bandwidth grows larger and larger, and therefore it goes to infinity, h of t is not bounded. But if we have a band limited system, the single values h of t cannot exceed the square root. And this is an interesting result in the theory of signals.